All right. Well, we'll go ahead and get started. Hopefully you had your breakfast and things like that. Now we can talk about the tree nutrition instead of our nutrition. There we go. Okay. So chapter 5, this is about tree nutrition and fertilization. So we're going to talk about requirements that the tree has and what the soils have to do about it. So we'll talk about those essential elements, and then we'll talk about fertilization as an objective, like we're trying to correct a deficit. We'll talk about the types of fertilizer that are out there, the methods of application, what happens if you put down too much, and how to determine how much is enough. So we've identified about 17 essential elements, and these are necessary for the tree to grow, develop, and defend itself and reproduce, things like that. So what are these elements? Elements, they're usually there in sufficient quantities in the soil or in the atmosphere in a natural forest setting. Remember that we as arborists tend to work with trees as individual trees, like out in our front yards, things like that, and not out in the forest. Because we're taking trees out of the forest and putting them into a semi-synthetic environment, we have to check to make sure that they really do have what they need. Urban trees may be growing in soils that do not contain sufficient available elements for their growth and development. Well, exactly what are these elements? So there are some that are needed in relatively large amounts and those that are needed in smaller amounts. So macro means large or the big picture. Micro means the small amounts or the small picture. Here, macronutrients, our largest one is nitrogen, followed by phosphorus, potassium, calcium, manganese, sulfur. And then, of course, we need the stuff in the atmosphere, the carbon, the oxygen, and the hydrogen. These are needed in relatively large amounts. The micronutrients out there, boron, chlorine, copper, iron, manganese, molybdenum, zinc, and nickel, are required in relatively small amounts. These small amounts out there are usually available in our soils. Now you say, well, when might they not be? Well, if we have a tree that should be growing in one place and we're scooping it up out of its native environment and then plopping it down in a totally different geographic area, the tree would have never have adapted to those microelements that are available in those soils. So you might have to add to it in order to get the tree to perform to its genetic potential. Again, macronutrients are required by the tree in very large quantities. Nitrogen is often the most limiting macronutrient and the one required in the largest quantity. I like to think about it as it's the limiting factor. Remember, there's all this chemistry that we talk about in the biology section, that is this chemistry that goes on in the background to produce photosynthase. So nitrogen would be like eggs in a cake mix. If you only have 2 eggs, it doesn't matter how much flour you have or sugar or butter or any of that stuff. It doesn't matter because you're limited by only having 2 eggs. That's kind of how nitrogen works. If nitrogen's not there in sufficient quantities, everything else begins to shut down and doesn't happen. In the urban environment, leaf litter is removed, which interrupts nutrient cycling. Most of the nitrogen that's found in the soil comes from the decomposition of leaf litter. So if we're raking up all of that leaf litter in the fall and bagging it up, or we're constantly every week we're mowing our yards, we're taking up the clippings and hauling them off, we're constantly removing those substances that should be recycled into the soil to give the tree what it needs. So you'll notice, especially on like fertilizer bags and things like that, you'll see this N, P, and K. And these are our 3 largest elements. This is nitrogen, potassium, and potash. So N, P, and K are required in these relatively large amounts. You'll see it on every bag of fertilizer that you ever buy. The letters will always be in those 3 in that order, N, P, and K. So after macronutrients, we have the secondary nutrients such as magnesium and calcium. These are kind of required in moderate amounts. They don't have to be there in super large amounts, greater requirement than the micronutrient. So again, nitrogen under natural conditions comes largely from the decomposition of organic matter. The removal of the leaf litter and all that sort of stuff disrupts that cycle. Much of nitrogen can be lost due to leaching or volatilization. Leaching means that it's going down through the soil profile. Volatilization means that it's being converted into a gas that's liberated into the atmosphere before the tree has a chance to use it. Nitrogen deficiencies are common in sandy soils and soils that are low in organic matter, especially if irrigation is heavy. So if you think about sand, it's a very coarse soil. If you poured water in it, the water is pretty much immediately just going to go to the bottom of it. Fill it with our Texas black clay that I have out in my front yard, or the red clays that are in Georgia, and the water is likely not to get to the bottom of your beaker for quite some time because it packs in so heavily. So if we were to add fertilizers on top of sand, when we water it in, it's just going to go through that profile. And so that would be leaching. It'll leach out of the soil. Nitrogen deficiencies are common in these sandy soils because, again, it just gets washed out. Nitrogen deficiency causes a reduced growth, smaller leaves, and chlorosis, or the yellowing of leaves. You're going to hear this term chlorosis quite a bit, and we're going to hear it because it produces this chlorosis. It's an appearance, and there's lots of causes for the yellowing of the leaves. But keep in mind that when you hear chlorosis, don't automatically think, well, it's a nitrogen deficiency. It could be not enough water. It could be too much water. There's just all kinds of things that can cause chlorosis, but just be cognizant of that as you study the materials. Again, then finally, we have the micronutrients. These are required in lesser quantities. And in fact, they might become phytotoxic at higher levels. So there's some there that it can bind in the soil to other compounds if it's there too high, and cause some toxicity to the plant material. Deficiencies of iron, zinc, and manganese can lead to serious plant health issues. So iron, zinc, and magnesium. We'll talk about how the molybdenum, copper, chlorine, boron, and nickel are very less likely to be deficient. Almost anywhere you go in the world, you will have some level of these elements, and they'll be there in the sufficient quantity for good plant health. Deficiencies of iron, manganese, and zinc can result in, guess what? Chlorosis. So if you don't have these, you can get that yellowing in the leaves. Just keep that. All right, so let's talk about fertilizer, the actual bag of fertilizer that you find on your shelf. So anything that has all three of these numbers, any of these bags with all three of these numbers, is going to be referred to as a complete fertilizer. So a complete fertilizer will have some amount of nitrogen, phosphorus, and potassium in the bag. And again, common way to say potassium is to say potash. So it's potassium, NP, and K. And it comes up with this K because in Greek it's spelled with it. The fertilizer analysis gives the composition of the fertilizer expressed as a percentage by weight of the bag. So when you see this 25-10, that means that 20% of the weight of the bag is going to be nitrogen. The 5 is 5%. The 10 is 10%. So what happens when you add all these numbers up? You get 30, right? So 30%. So only 30% of this bag is actually a fertilizer, right? So what's the rest of it? It could be sand, it could be organic matter, it could be something that they use to encapsulate the NP and K. So it might not necessarily be inert, but it doesn't contribute to NP and K. So again, an example here, so a 50-pound bag of complete fertilizer that reads 10-10-10 contains 5 pounds each of nitrogen, phosphorus, and potassium. A lot of people ask, is there going to be some mathematics on this test? And the answer is, well, kind of, yes, there will be some mathematics. It's not going to be complicated, but you will have to think about it. So prepare yourselves, and they could ask the question in different ways. So if this were a 50-pound bag, a 100-pound bag instead of a 50-pound bag, how many pounds of nitrogen would it have? Well, it would have 10 pounds. Since it's a 50-pound bag, in this example, it only has 5. So be prepared for those questions and pretty much any permutation you can think of. So trees, however, trees seldom need a complete fertilizer because nitrogen may be the only limiting factor. So it would be common to see something more like this 23-3-20, where it's not, all 3 numbers are not going to be the same. In Georgia has very high phosphorus, so it's quite common in Georgia to see this number be fairly low. In fact, it could even be a 0, like 21-0-20 or 21-0-15. So you can purchase these with all different types of numbers. You can also purchase it as just a nitrogen source, just a potassium source, and just a phosphate source. So you could get it and then mix it yourself to create a custom blend. So we like to only apply phosphorus and potassium as a soil test indicates. We'll talk a little about soil testing and what that can tell us. There are different types of fertilizers out there. We have organic and inorganic fertilizers. So under organic fertilizers, we have manures, sewage sludge, bone meal, cottonseed meal, and then synthetic organics. So you might ask yourself, what is a synthetic? Most of our modern day fertilizers that we use in the tree care industry are going to be a synthetic organic type, unless you run an all organic type. But these can be urea formaldehydes, methylene ureas. They are long polymers that are chains nitrogen. And so, based on a carbon molecule, so it's organic. Remember, gasoline is organic because it's an organic compound. It's a carbon-based compound. Organics would be the other classification of fertilizers. Inorganics include granulars, things like Miracle-Gro, and encapsulated slow-release fertilizers. Encapsulated means that it's covered in something like, you've probably seen the bags of fertilizer, and it has like yellow and blue and orange dots of these little, what they call pearls, that we distribute throughout the lawn using a spreader. What gives it that color is whatever the coating is. And the coating could be sulfur coating as a good example. It's a common coating. So the thickness of that coating, the water can erode away that coating to the point where it eventually releases that carbon compound or that nitrogen compound that's being encapsulated by it, and the tree can use it. So that's how they produce a slow release fertilizer. It erodes away with water. Whereas these synthetic organics that are slow release fertilizers, these are those polymers, and it literally takes a soil microorganism to chew that carbon bond off to release it. So it doesn't really have much to do with soil moisture or rainfall as this type of slow release does. So we need to talk about the rates of fertilizer. So we've talked about the percentage of fertilizer in the bag, but now we have to express that as how much of that weight is distributed over a certain amount of area. Like a rate is like miles per gallon. This could be pounds per 1,000 square feet. So that's a rate. The rate of the fertilizer to be applied should depend on the tree's age, the health, the species of the tree, what type of fertilizer that you're using, the method of application, and the site conditions. Slow release fertilizers reduce the amount of nutrients that can be leached and also reduces salt and fertilizer burn. We'll talk a little about fertilizer burn, but what that is that you've created such a salty area out in the soil that water is going to move from this area of high concentration to an area of low concentration. So it's going to want to move out of the plant into the soil, which can cause the trees to burn up. You can also get too much nitrogen up into the tree. And again, the tree has no choice but to consume and utilize that nitrogen. It can't just store it as nitrogen. It's going to use it. And so you might drive the system so fast that it can't keep itself cool, and then the leaf burns. Fertilize with a slowly soluble source with at least 50% of the nitrogen in the form of water insoluble nitrogen, or WIN, water insoluble nitrogen, that has a salt index less than 50. This is, we talked, or I spoke briefly about those ANSI standards in our first lecture. In those ANSI standards, there is one about fertilization, and this is part of that standard. So you very likely see a question like this on the test, especially this part about the salt index less than 50. What that index refers to is the accumulation of salts in the soil, application. If a salt index is less than 50, that means it's really not going to build up in the soil. The cheaper your fertilizer, like just the straight urea nitrogen sources, urea is a binder for that nitrogen. So you take the nitrogen out of it, and you're left with a salt, and that salt accumulates into the soil, and it can accumulate to the point where nothing will grow in the soil anymore. So that's why you want to use fertilizers with a salt index less than 50. In general, the recommendation for slow release fertilizer is 2 to 4 pounds of actual nitrogen per 1,000 square feet of root area. Remember when we talked about that bag, that 10-10-10 bag, and it's a 50-pound bag, we only have 5 pounds of nitrogen in that entire bag. So this is what we're talking about. So when they say actual nitrogen, what they're saying is, what percentage of the whole bag is actual nitrogen. So when they say 4 pounds of that, if we had that 50-pound bag, we would use almost that entire bag in 1,000 square feet to get 4 pounds of it. Hopefully that makes sense to you. Quick release fertilizers should be 1 to 3 pounds of actual nitrogen per 1,000 square feet, not to exceed 4 pounds annually. So any of you that might have a turf program and they're doing fertilization on your turf, they might come out 4 or 5 times a year to do fertilizer applications. And what they're doing is they're putting down very low amounts. They're putting down anywhere from 1/2 to 1 pound of actual nitrogen, but they're doing it 5 times a year. So they're staying at or under that sort of maximum target of 4 pounds annually. So where do you think this 4 pounds of actual nitrogen over the course of the year comes from? Well, glad you asked. So they did all these studies out in the forest where they're digging through the leaf litter, how deep are the leaves, that sort of stuff. And they calculate how much per square foot that amount of leaf litter can create over the course of a year. And guess what? It turns out to be about 4 pounds of actual nitrogen that the plant can use. So what we're doing with this 4 pounds is we're mimicking what would naturally be available in a forest environment. So is timing important? Well, it can be fairly critical. Nitrogen uptake peaks during the spring and the summer months. The most limiting factor in fertilizer uptake is water availability. Remember, whether it's a quick release or a slow release, in order to get it out of the soil and into the root of the tree, it has to be dissolved in water. So right now here in Central Texas, yesterday we had our first rainfall since June. We haven't had more than 1/4 inch of rainfall since June. Yesterday we got the rainfall, so we all celebrated. It was awesome. But is it moving any nitrogen during that period? And the answer is no, because once it plays the moisture out of the soil and go into these drought conditions, the tree's really not going to get anything out of the soil because it can't be dissolved. Soil type also helps to determine how often to fertilize. Clay has what we call a high cation exchange capacity, or CEC, and less frequency is needed than in sandy soils. Because of that high CEC, it can really bind that stuff into the soil so it doesn't leach out or volatilize into the atmosphere. Unlike sand, where if we fertilize it, that fertilizer is going to perk down through the layers of the sand and eventually get below our roots or into the water table and disappear. So clay soils have a high cation exchange rate and hold more in the soil. So therefore they need less frequent applications. In sandy soils, you're going to need more frequent applications. Fertilizer uptake is greatest during active root growth. So notice this nitrogen uptake peaks during the spring and summer. If my spring and summer conditions here in Central Texas are going to be much different than those, say, on the California coast or in Canada or Minnesota, where the soil temperature is never going to get into the 80s and 90s. Here our soil temperatures are into the 90s and pretty much all microbial activity stops. And so there's not going to be any root activity without microbial activity. So ours here specifically, remember this is an international exam. So internationally speaking, our nitrogen uptake is going to peak during spring and summer, because that's when the roots are going to actively be growing. But if you look at a very specific region, it could be different, such as here, our fertilizer uptake is going to be greatest in the spring and then early fall. Apply quick release from spring through. Remember that when you put down a quick release, it's not going to last very long, especially the nitrogen portion of it. It might only last days to a few weeks. The slow release formulations can release, as an example, a UF or urea formaldehyde formulation of a nitrogen source, can release into the soil based on microorganisms, I'll get it right, and activity over a period of 10 months or even longer. Or if you've got, the closer you get to the equator, the more activity you're going to have, and it could release in 6 or 7 months. But in general, it's going to be about a 10-month release period. And so that's why you can really apply these slow release fertilizers nearly any time of the year. The quick release ones are going to apply it when there's going to be rainfall. So spring and fall. These things are just going to sit there and do nothing in the winter. So what are our application techniques? How are we going to get these fertilizers actually into the soil? Our surface application is generally the cheapest, most effective way. It has lots of advantages. If you're just going to spread it over the top of the ground, it doesn't take any sophisticated equipment, other than something that you can, some method that you can calibrate so that you make sure that your application rate is the proper rate. Effective at providing nitrogen to trees, yes. It requires the least amount of time to do, yes, because you're just walking on the surface, distributing a dry type of fertilizer, or a hose, you're just spraying it onto the top. It's applied in the location with the greatest amount of uptake. It's the tree roots are going to be right there at the surface, because remember, that's where there's air and moisture, which are the two things required for root development. So you're going to put it right there in the upper 6 to 12 inches. It's the least expensive. However, it has a greater potential of volatilization, or it could run off. So they have here, in other words, runoff in the nearby rivers and streams, but volatilization has more to do with it getting into the atmosphere. And so anytime you have it on the surface, you're either going to lose it on runoff, or you could lose a bunch of it to the atmosphere. Here's a couple application devices that are common. This one is handheld. It's often used to do shrubs to work your way sort of in and out of difficult areas. You've all seen this sort of standard drop fertilizer. Fertilizer's in this hopper and drops down onto this spinning disc, and then that disc sort of sprays it out to both sides 4 or 5 feet. And so you walk in a nice straight line and you're going to distribute the fertilizer. It's great for grass. It's pretty good for trees, as long as all the conditions are right. Our next type is what we refer to as subsurface application. So we're either going to have a surface application, a subsurface application, or a foliar application, or you could also have a trunk injected application. So there's really about 4 ways to get it into the plant. The subsurface application places the fertilizer below the surface a little bit. So we're not going to have as much volatilization, and we're not going to have runoff. We can still have leaching, but it's going to be minimized. Remember that grass roots are going to grow downward and tree roots are going to come up to it, and they don't want to overlap a whole lot. They're getting close to each other like this, where the root tips get close, but they each produce a chemical that retards the development of the other. So if you have a heavy grass or turf area that comes all the way up to the trunk of your tree, doing a surface fertilization is not going to do much more than just fertilize your grass. So you're going to want to get it underneath those grass roots and down where the tree roots are. And so the subsurface application is perfect for that. One way to make this happen is what's called the drill hole method. You're literally going to drill a hole 2 to 4 inches in diameter, and about 12 to 18 inches deep, and they're going to be 36 inches apart on a grid pattern, all underneath the drip line of the tree, and even extend a little past the drip. And then you're going to fill that hole up with maybe a granular fertilizer or pre-mixed liquid. So that's another advantage to this type, is that you get partial aeration of the soil. Remember, you're drilling a hole, so you're going to remove some of the soil, which allows the surrounding soil to collapse a little bit, which is going to aerify a pretty large area. Where exactly is this treatment area? Where should we be making our applications? So we can see that this area underneath the tree is our target application area. Our crown radius, so we're going to say crown radius R, so that's going to be from the trunk of the tree out to the drip line. And notice that this treatment area is a little bigger than that. So they have 1.5 times the crown radius should be our treatment area. So if this is 10 feet, then this would be 15 feet. So the other type is a liquid injection method. You can use, again, these same drill holes. The holes are drilled 4 to 12 inches deep, 12 to 36 inches apart. Fertilizer is dissolved or suspended in water and injected under hydraulic pressure into the soil using a soil injector. So you don't even have to drill holes. The most common way to get into the soil is what we call a soil probe. So you have this case hardened steel with a point on it. The point has little smaller holes in it. You're going to jam this thing down into the soil, and behind it you're going to have a tank, and you're going to have 150 to 200 psi solution, your fertilizer solution. You're going to have a little valve that you open the valve up, or there's multiple ways to do the valve, but you're going to open the valve up and you're going to put in some amount of fertilizer, and you're going to do this on a grid pattern under the tree. This is much quicker than drilling holes, and it works very, very well. The biggest advantage is that you get better distribution of the fertilizer in the root zone, plus you're adding water to it. So anytime you have water, you can dissolve more stuff in the water that you're injecting, and then the root has the ability to take it up. So remember, without water, there is no uptake. You can also do a foliar application. Think about this as a cream that you might put on your skin and be transdermal, so it's going to move through your skin and into your vascular system. Same sort of thing happens with trees. When we spray fertilizers onto the canopy, it's absorbed through the leaf, and the leaf can use it immediately. It's very easy to burn plant material this way because you're getting it right there to the where it's going to be used. There's no loss in the system. There's no feeding of microorganisms in the soil. You're putting it all directly to use. So the rate for a foliar application is going to be much different than the rate for a soil application. In fact, typically we don't like to use any nitrogen at all, but we will use a foliar application to correct a micronutrient problem. Something such as iron. Iron chlorosis can easily be corrected with a chelated iron spray. This can be expensive. It can require specialized equipment to be able to spray very tall trees. Again, this is an international exam, so here in Central Texas, our trees get to be about 75 feet tall. In Georgia, they get to be about 110, and out in California, they can approach 200. So it really depends on where you are. It's going to be very, very difficult to spray the canopy of a 200-foot tall tree. It would require very expensive and specialized equipment. And again, our common thing here is like a chelated iron spray. It's going to produce a very rapid to a chlorotic problem. It's going to be fairly short term. And again, it's not a good way to fertilize for a nitrogen deficiency because it's just too easy to burn the plant. Again, I talked about the trunk injections a little earlier, or alluded to them. They come in micro injections and macro injections. They are implants, or they could be an implant, or they could be an injection directly inserted into the xylem of the tree. So you're going to drill a very small hole. You're going to put a tube or a needle or something into that hole, and then through that you're going to push in whatever micronutrient or macronutrient the tree might need. It does rely on the transpirational stream to move material systemically within the xylem tissue. So, we've done insecticides this way. Some of them can move very rapidly through the canopy of a tree. As an example, we've injected a 20-inch red oak tree in the springtime with lots of rainfall on a windy day. And we've moved a product throughout the entire canopy, and we're starting to see caterpillar die off in 15 to 20 minutes. So it can move rapidly throughout the tree. However, if the tree decides, well, I've been watered for days, I don't really need water, I've made all the photosynthate I need to make, maybe I'm just going to chill out today, then sometimes that injection might take all day. So it could take anywhere from minutes to hours and hours. It is a good way to get in and restore micronutrient balance. It does require this transpirational stream, so it's not good for trees that are under drought stress. Again, the tree doesn't have a choice but to take in this product because you're putting it in under pressure and the tree has to do something with it. So it's easy to throw an imbalance, like the tree might not be getting in enough water to go with all these nutrients that you're giving it. And so the concentrations by the time it hits the leaves are very high. And so it can burn the leaves off. So you would not want to use it in a drought stressed condition. It does require proper technique to apply products this way. It does some damage. And so every time you wound a cell, remember wounding is killing when it comes to plants. So when you drill, you're actually going to kill some of those cells that are not going to be replaced, so you're introducing the possibility of decay. So it's not something you want to do every 6 months. It's probably not even something you want to do every year. In fact, the preferred minimum is application every 2 years. Let's take a look at what this looks like. So these are the capsules. These are injection capsules. There's a little hole that's drilled. Then this piece is called a pick. That pick is placed into the hole. This canister is attached to the end of that pick. And then you hit on the back side of this and it cracks a seal. And these things are actually in two parts. They're about twice this high when you first put them in. And you squeeze the top part into the bottom part so that you get about 9 to 10 pounds of pressure built up inside of here, which gives you about 1 pound of positive pressure to push it into the tree. As you can see, each one of these holes does have some wounding, and the wounding tends to go up and down the tree, up the tree 4 or 5 inches, side to side away from these picks, about 1/2 inch or so. So if we're putting these in place about every 6 inches around the tree, and I came back the next year and put them in between at the same height, the tree has not really grown enough. So now we're really soil and plant uptake. Here's some additives that we can add to our formulations, our mixes. These things have become very popular. We can inoculate the soil with fungal spores to encourage mycorrhizal development. And a lot of people say, well, does this mycorrhizal stuff really work? Does it do its job? Well, it's been proven to work in specific environmental conditions. Our first one that became available to us was called a PT mycorrhizal spore, which stood for Pithelicus tinctoris. With this particular type of mycorrhizal spore, it was found in these really harsh soil environments, these really low soil pHs in low organic matter areas. They found them around strip mines is where they found it, or borrow pits where the topsoil had all been removed, but yet these trees were growing and we're like, how can this happen? And so they isolated a very specific type. They've since gone on to identify more types of mycorrhizae, There is, I think, when we were looking at those slides in the biology section, we showed the mycorrhizae, so that PT or Fertilizer tinctoris. That's actually what you saw in that slide. It has that big sort of antler-looking structure to it. There's also endomycorrhizae that occurs in plants like dogwoods and sycamores and diffuse forest trees, most diffuse forest trees. So, these things are they gonna always work? No, but we put in a bunch of other stuff with it. So we add lots of soil microbes. So this is the bacteria, the strep. Yeah, there's tons of strep in the soil, beneficial types. We're also going to add organic matter, because what do these soil microbes eat? They eat organic matter. We're also going to add some microelements such as vitamins and minerals. One of the big things that we discovered is seaweed. Seaweed is just loaded with cytokinins. If you think about what seaweed has to do, it's out there in the ocean, wave action breaks it apart, it floats around, and as soon as it touches ground, it needs to be able to push roots out so that it can keep growing. So it has all these rich cytokinins there so that it can just explode roots into the soil when necessary. Well, we can use that same seaweed in a soil injection mix and get a similar type of response, root development, right? So if we're having difficulty growing roots, such as a construction environment or compacted soils on college campuses, things like that, seaweed can be very effective. Another byproduct of seaweed is that it acts like a surfactant, and it helps to break down the barriers for water absorption in the soil. So we take all of these things and we mix them together, and we know that each individual thing works, but it doesn't necessarily work in every environmental condition or every instance. And so that's why this last statement is here: limited research and evidence of efficacy. It's because, yeah, something's working, but we're not real sure what's working. So just keep that in mind, that have a very specific use if you're going to use these additives. Know why you're doing it. What's my prescription? When you're doing fertilization, you should do it with intent, not just a blanket application. Water, leaching, salt content, and pH may limit the uptake of certain elements. So that's just going to get us into a prelude here of the effect of pH, which I talked about a little earlier. Very high or low soil pH may reduce the availability of elements. If the soil is too alkaline, iron may become unavailable. If the soil is too acidic, magnesium may become unavailable to the tree. Now, you've probably seen this chart before. This isn't going to be the first time or the last time that you see this chart, but you might not have ever really understood what this chart is telling you. So I'm going to try to get this point across to you. Across the bottom of this chart, we have the pH, and above it, we have what's going to happen, or as far as availability goes, at that pH range. So this is effective nutrient availability. That means how much of it is available to the plant. So there might be very large amounts of iron in the soil, but here you can see that a low pH on the iron. See how wide the bar is on iron? The width of this bar means how available it is. So at pH of 4, iron is very available to the plant. But if we go in the other direction towards alkaline, as we approach 9 out here, iron becomes relatively unavailable. However, there's this, if we were to chemically measure how much iron is in the soil, it would be the same regardless of pH. The weight of Fe, iron, in the soil is going to be the same. However, because the pH changes, different amounts of it are going to be available to the plant material. Now notice this blue bar in the background. This blue bar is sort of the optimum, the Goldilocks zone, where they're all available in relative amounts that are nutritionally acceptable for the plant material. This dark bar here, this 5.5 to 5.75, That's sort of the optimum. So if we could choose a pH that's going to grow the plants best, it would be sort of in this area. However, trees function very well throughout this 5.5 to 6.5. I think Kay in her soil section, if she hasn't taught it already, she will. You should know by now that these are compounding, they're logarithmic. They're not linear. So pH is not linear function. Right, so salt problems. Remember, we talked a little about this. Fertilizers are salts that come about from different chemicals. Fertilizer burn is the result of excessive soluble fertilizer in the root zone. Symptoms range from wilting and marginal burning of the foliage to overall plant death. If we use a fertilizer with a salt index less than 50, we're not going to get salt burn as a result of repetitive use. Slow release fertilizers are less likely to burn as they're releasing over a longer period of time instead of instantly making 100% of it available. Leaching is the washing of chemicals down through the soil. So soluble nitrogen tends to leach and can be harmful to the environment. Most of our products that we use in the house, in our homes today, have almost no phosphate in them. You know, back when I was a kid, phosphate was in every hand soap and dishwashing liquid and laundry liquid that you could find. Does a pretty good job of helping to clean stuff. It's an excellent surfactant, but so much of it was leaching out into the environment, into our streams and lakes and ponds and all that, and it grew algae like crazy. So much so that the oxygen levels in our water environment began to drop, so they banned it from our use. So it's not, we don't see it happen very often. However, it can still get into our water supply in the form of fertilizers. So that's why we want to use only the amounts that we need. And then, of course, avoid overwatering in sandy soils because you're just going to wash it out before it gets a chance to be used. So we're going to talk about a soil analysis. That means we're going to take a very close look at the soil to see what a plant actually needs. I've talked before about creating sort of these 10 by 10s, and we can make that 10 by 10 Excel file available to people that might want it. You should know what your tree needs. You should know that a white oak in your particular soil environment needs a certain amount of these elements to stay nutritionally satisfied. And so how do we know if our soils are producing it? The only way we can do it is through a soil analysis. And with a soil analysis, we can formulate or prescribe a fertilizer. That means we're going to come up with a specific mix that plant needs in that environment. So the soil analysis is the most accurate way to determine the needs of the plant. What is a soil analysis going to give you? It will give you information on soil pH. It'll tell you about the essential elements. It'll tell you about the percentage of organic matter, and it'll tell you the cation exchange capacity of that soil. When taking soil samples, it's very helpful to fill out the form before you submit it and tell the scientist, tell the lab tech what you're growing. Are we growing grass? Are we growing trees or something else? Tell them why you want this test. You're going to sample the soil from a very large area. We call these samples cores. We have these metal rods the hollow rods, we jam our tubes, we jam them into the soil, and it pulls this sort of core of soil out. And you want to be in the active soil profile. In other words, you don't want to go down below 18 inches and sample soil down there because there's not going to be very many roots there. So we're going to want to sample in that top 4 or 5 inches, 4 or 5, 10, 11 inches of the soil. You're going to throw out the grass that you collected at the top of the plug, throw that away, and then take the rest of it and put it into a big bucket or a dish pan or something like that. You're going to pull cores from all underneath the tree. some out by the drip line, some on the high side, some on the low side, some closer to the trunk, some in the middle. Take a bunch. You're going to get a better average of soil the more samples you take. And you're going to put them into this bucket. You're going to mix it all up, and then you're going to scoop out just the amount that the fertilizer analysis bags are fairly small, and they'll have a line on the bag that says, fill to here. So you're going to scoop it out of that bucket and put it in that fill to here, and then seal it up and send it in. And then in a few weeks, you'll get back your answers. You can also do what's called a foliar analysis. You can take some of the leaves off of the plant and send these leaves in. This works best in conjunction with a soil analysis. So you can take a soil test and a tissue test and send those in. Representative leaf samples are dried and analyzed for nutrient content and compared to target level for the species. So you're really, what is a representative sample? For those of you who are in all these tree groups on Facebook and places like that, I'm sure you've got these ads that show up in your feed for this little device that you clip onto a leaf, and it measures the nutrient content of the leaf using light. It looks kind of like one of those things you put on your finger to measure dissolved oxygen, O2 in your bloodstream. So you're taking it, you're clipping it onto a leaf. But one of the interesting things that they discovered playing with this tool is that the nutrient content of the leaves at the bottom of the tree are significantly different from those at the top. And those that are out at the tips are significantly different from those on the interior. So it can vary throughout the canopy. When I first started in this industry, we didn't have stuff like that. So we just grabbed things from around the bottom that we could reach by hand, not knowing that we needed to climb the tree and get some from all over the canopy to send in. So it's just sort of a neat thing that's come about. This can be very helpful in the diagnosis of certain deficiencies. Remember we talked about chlorosis and chlorosis having a lot of different causes. This would be one way where you could help isolate one of the causes of that chlorosis. So that is the end of this chapter. So we're going to take a break. But remember that, if you have specific questions, feel free to email me. Here's my email address. Just put something in the subject line so that it doesn't go to my spam folder. But I'll be happy to comment on anything that I present, as well as anything that's presented by Kay. So feel free to ask.
Okay, awesome. Thank you, Rob.
All right, so diagnostics and plant disorders. This is sort of an interesting topic. This is one that's very dear to me. This is most of what I do is plant healthcare in my business. But again, this is something that varies across the globe and in different places. So, when you go to actually practice this type of diagnosis and plant disorders, think about it locally, and again, remember how things should be in order to know if they're right or if they're wrong. So we're going to start with breaking it down by the causes. Is it something that's alive, or is it something that's not alive, non-living or living? The diagnostic principles and approaches, we'll talk about stress, the different signs and symptoms, similarities and differences of tree disorders. Again, biotic and abiotic, living or non-living, physiological disorders and injuries and their treatments. And then insects and diseases, their treatment. So let's think about, how can you begin to identify? If you're walking through, remember we talked about chlorosis, that sort of yellowing. If you're walking through an area and you see tip decline in the canopy, your first thing is to say, well, what's the cause of this tip decline? Is it something that's living or non-living? So if we're thinking about those things that are living, otic disorders are caused by a pathogen, such as fungi, bacteria, viruses, phytoplasms, nematodes, insects, mites, animals of some type. They are typically infectious because they can spread from one plant to the next. Here in Texas, oak wilt is a very big problem. And oak wilt can spread through either root grafting or can be vectored in by a beetle, the Nematodes beetle. So there's multiple ways for this problem to get into a tree. but it can spread tree to tree to tree, and usually goes from oak tree to oak tree. So it's really not going to get in ash trees or things like that. So it's isolated to a particular species, and it moves, it looks infectious. Some things can throw you off. They can appear to be infectious, but in reality, they're not. Soil compaction is a good example. It can look like you have a bunch of trees with tipped dieback in the canopy because the soils are compacted. It can look infectious, but if we take a look closer, we'll notice that when it comes to compacted soils, that it impacts all the trees, not just one species. Some abiotic disorders. These are non-living disorders. These are typically environmental problems. They are non-infectious. They're not going to get outside of the impacted area. Your impacted area is not going to grow any. However, you can have things like temperature extremes, mechanical injury from humans, chemical injury from misuse of herbicides, pesticides. You can have mineral, drought, and flood conditions all contribute to abiotic disorders and are non-infectious. So this is an area that's just down the street from me. A few years back, we had a freeze that was a record freeze of all time here in Central Texas, and it created lots of damage to our trees. Live oaks have the ability to live in temperatures that are fairly cold. They get down to around 4 or 5 degrees. However, we had -5 degrees for more than 10 hours here where I live, which should be enough to have killed every tree. It didn't really kill every tree, but did impact them. So here's a tree that has some impact. It's thinner than it should be. Again, this is a live oak. Here's another live oak. See all the tip declines? This is all vascular damage from the freeze. The water inside of the tree froze, expanded, and as it expanded, it destroyed the xylem tissue. And from the point where it was destroyed towards the tip, the tree died. And we saw this type of vascular damage anywhere from the tips to the actual on the main trunk. Some of it were on the large leaders. There are some other trees. This is an example of an ash tree. It killed almost all the ash trees. So if we were looking at this from, is it abiotic or biotic, it would be a little more difficult to tell, because if we were to use a drone and look around the area, we would see widespread damage to ash trees and live oaks. And so we would think, okay, well, there's some disease at play here because it's just impacting these two varieties. But living here and knowing what we experienced, it was easy for us to determine that this was an abiotic disease. I mean, abiotic problem, but if you were just to be dropped in and had to diagnose this from the get-go, it would be a little more difficult. And here's a good example of the bell curve. We talk about hardiness zones. This is a good time to bring this in. Again, these trees, these are both live oaks. They both experience the same weather environmental conditions, but because they are genetically random, these are not cloned trees. These are naturally derived from acorns. You can see that the temperature greatly impacted one and not the other. And you might say, well, Rob, this is chemical damage. I can tell you that it's not, because I've looked at hundreds and hundreds of these trees in the similar circumstances, and this is just pure genetics. So they say that, when you look at that hardiness zone and it says, it's rated to 5 degrees, that means the majority of the trees are going to survive 5 degrees without impact. However, you go to 4 degrees and they're going to start dying. 0 degrees, there's going to be a bunch of them die, but obviously at -5, you still have some that this tree has died since I took this picture. So we'll talk about some general diagnostic procedures. A complex is something that is a combination of stress factors. It can be biotic and abiotic. We could have abiotic stressors such as soil compaction that creates an environment of stress for that tree. The stress hormone is ethylene. So ethylene might be emitted into the atmosphere, which might attract ambrosia beetles. And so then the tree would go into decline, from decline and death from that combination of stressors. Non-specific symptoms. Avoid concentrating on the symptom instead of the cause. It's good to take in all of the symptoms and then start to look for a cause. I've done this for over 30 years, and sometimes I want to jump to a conclusion. Like I go to a new site and I see something and my brain says, well, this is a construction site. I have tip decline up here. It must be soil compaction. Avoid making that leap until you've taken in all of the information. You want to go and look at the whole site. We'll talk about a systematic diagnosis in just a second, but avoid jumping to that conclusion. 70 to 90% of all plant problems result from adverse cultural or environmental conditions, such as the wrong tree in the wrong place sort of scenario. And I always stress, don't guess, know when to ask for help. I have a network of friends in the industry throughout the world, and when I come across something that I can't diagnose, I'm more than happy to ask my friends, have you seen this before? Do you have any idea what this might be? Do you have someplace I could look? Or is this something new on the horizon? It shouldn't impact your ego if you can't answer these questions. So just don't guess at an answer, because solutions oftentimes can be very specific. And if you treat a tree for something that's not on the treatment product's label, well, that's illegal. Plus, you might be treating it with, say, a fungicide when it's not a fungus, and fungicides are very expensive. So not only are you putting fungicides into the environment, but you're wasting a lot of dollars and time for your client. Yeah. So have a systematic way that you approach your trees. One, accurately identify the plant or tree. Know exactly what it is that you're looking at. Am I looking at a white oak, a swamp white oak? Am I looking at a northern red oak? Am I looking at a southern red oak? Am I looking at a bastardization of a red oak? Know the plant that you're looking at. Know how it should be so that you can identify normal versus abnormal. Number two, look for a pattern of abnormality. Is it uniform in the canopy, or is it isolated in the canopy? Is it something you just see on the trunk? Is it something you just see on the roots? Number three, examine the site history. We as diagnosticians are often asked to come up with a solution with a single look at the plant. I go out to a property and I stare at the tree and I see these problems, but I have no idea what's happened. And so I interview the steward of that tree. What's the past? When was the last time you had construction? And you have to pose your questions in such a way as to eliminate bias from their answer. People often don't know what you're truly asking. I might say, has there been any construction on this site? And in their mind, they're thinking, man, I haven't done anything in 6 months. No construction whatsoever. And so I always say things, have you had any construction in the past 7 to 10 years? And then they say, well, no, I haven't had any construction in the last 10 years. And then I'll say something like, well, construction might include replacement of water lines, sewer lines. Have you had an irrigation system installed? Did you have a drain field installed or repaired? Things like that. And then suddenly they might say, well, yeah, 4 or 5 years ago, we did do X, Y, Z. So it could give you some more history there that they wouldn't have given you just automatically. Another thing to ask about is, do they have a turf service? Someone treating that turf? Do they have a tree care company already and they called you out for a second opinion? Ask them, have you had another opinion? Has someone else already looked at it? Why did you have them look at it? How are they, how are you connected to them? Have they done, I had one site where there was all this herbicide damage, and I kept thinking, man, there's a lot of herbicide damage here. But we went to the turf company and looked at their records. Their records were great. The properties before and after this one were fine. I couldn't really find anything. And then the husband said, well, last fall I did use a lot of Roundup around the base of the trees to try to kill some of those weeds that I couldn't get with the mower because I know mower damage is bad. I'm like, well, how did you mix your Roundup? He goes, well, I just used it straight out of the bottle. So he was using a concentrate right around the base of this tree and damaged all of his trees. But I wouldn't have found that out without examining that site history. So try always to get that site history stuff. Examine the foliage color, the size, the thickness of the leaf. Leaf symptoms may be caused by problems elsewhere. In the construction or the tree conservation world, Cambistat, which is a growth regulator, is commonly used. Cambistat can be used by the builder, by the developer, by the homeowner before all of this has begun. So there's a number of ways that a contractor could have gotten in there and applied this product. It's an excellent use of the product. However, it makes the tree look a little funny for about 7 or 8 years. It causes the leaves to be a little thicker and about 30% smaller. And so when you look at it, you're like, man, the tree just looks kind of funky. And that's often the reason why on a construction site. So again, getting that site history can tell you a lot. Check the bark, the trunk, the branches, canker, wood rot, borers, bark beetles, water sprouts. Examine the roots, the root collar. Look for, get some of the small roots in your hand. Pull the sheath off of the outside of the root and look and see, is it white? Is it brown? Exactly what color is it? Get some of the soil and you can smell the soil. If it has a bad odor that's really strong, it could have become an anaerobic environment. It could be watered too much or something such as that. So it could be aerobic or anaerobic. When it comes to these last 2 items, I always tell people, do it the same way every time. The way I do it is, here's my tree. And I'm going to start way out here, and I'm going to look up at the top of the tree, and I'm going to look at the landscape between myself and the base of the tree. And then I'm going to walk myself around the tree, spiraling closer to the center or closer to the trunk. And as I make that spiral around the tree, I'm going to start at the bottom. I'm going to look down at the ground, then up into the structural branching habit of the tree. Then I'm going to look at maybe some surface roots. Then I'm going to look at the trunk, and then I'm going to look at the basal area of the tree. And so I'm doing it the same way every time, and I'm trying to get a 360-degree look at the, because I might find things in one area that I wouldn't find in the other. And I do it the same way every time. And again, avoid saying, oh, wow, I see on the trunk here as I walk up, I see the bacterial wetwood on the trunk of the tree. So I'm going to ignore everything else that's going on. Try to avoid doing that because, again, a lot of these are complexes. So there's one thing that's caused another, that's caused another, that's caused another. You wouldn't take all that in. So symptoms. Arborists must look for symptoms or effects of the causal agent that are apparent on the tree, or how the tree responds to the disorder. Things like chlorosis, wilting, leaf scorch, defoliation, branch dieback. Branch dieback could be caused from lack of soil area. It could be caused by soil compaction. It could be caused by, as we saw earlier, freeze damage. Defoliation can be caused by insects. It can be caused by hail damage. It could be caused by heat. So these, especially symptoms, have lots of causes. So it's not a specific cause. I can't look at this chlorosis and say, oh, that's an iron deficiency, because it might be a magnesium deficiency. It could be a nitrogen deficiency. So these are what we mean by symptoms. These are things that we quickly can observe, an effect that we can quickly observe. Compare that to a sign. Signs are direct indications or primary or secondary causal agent, such as we see a conch growing on the side of the tree. So we see this Ganoderma conch here on the side of the tree, and we say, oh, wow, but does this conch actually cause the problem? No, it's a sign of the actual Ganoderma fungus that's active inside of the tree. Another thing would be frass. So if we saw, what looks like sawdust at the base of the tree or cornmeal at the base of the tree, and we look up from that, we see a little hole going in, we can say, oh, there's a borer at play and it's injecting this stuff out. So It's a direct sign of the cause. We might see emergence holes. We say, why is that a big deal? Well, if you think about the emerald ash borer is a pretty good example. The emerald ash borer, when it comes out of the tree, it makes an exit hole that looks like a D. It faces up, so the bottom of the hole is flat and the top of it is curved. So that's a very distinctive exit hole as compared to one that might just be round, like a flathead borer might have just a round emergence hole. You might also find discarded skins. A lot of times when borers are inside of a tree, it might be the pupal stage and it's ready to reach adulthood, so it comes out to that exit hole and then it shucks its own. The difference between symptoms, so these can have multiple causes, and then signs, which have very specific causes. So if you can find signs, that's going to help answer your questions much more precisely. So what are the common tree disorders out there? We have blights, cankers, and chlorosis, decay, dieback, gall, gummosis, leaf blotch, leaf spot, necrosis, powdery mildew, rust, scorch, stunting, vascular discoloration, wilt, and witch's brew. These are all pretty common. You'll find these things around the world. You'll find them out in nature as well as in the urban environment. And so know a little about what each one of these, know how it behaves, some signs and some symptoms that go with each one. I talked about my 10 by 10 earlier, and that's where I take my 10 most common trees. And for each one of those trees, I find out 10 most common problems. What are the most common insects that attack this tree? What are the most common fungi that attack this tree, or bacteria that attack this tree? So come up with 10 things about 10 trees and put that in your 10 by 10. So if I have, oak wilt is a big problem here in Central Texas. So in my 10 by 10, I might have live oak, and then I'll have oak wilt. And then on the oak wilt, I'll describe what it looks like. Do I have vascular discoloration as a result of oak wilt? So try to develop these 10 by 10s on your own for wherever it is that you practice. Practiced in Georgia for the better part of 28 years before moving to Texas. And so I have information about my trees in Georgia. I do a lot of consulting in the Carolinas. So I have a 10 by 10 for the Carolinas. I have a 10 by 10 for Central Texas, a 10 by 10 for East Texas, because it's a totally different environment. So try to come up with your own 10 by 10 for wherever it is that you work. But think about these terms, what they look like, what they mean, so that when you're using your 10 by 10, you can use this vocabulary. So let's talk about stress for just a moment. Any condition that causes decline in a tree's health is a stressor. And there are a lot of stressors. There's so many stressors that sometimes I'm amazed that trees live. But obviously they're very durable organisms. But stresses are thought about as acute or chronic. A good example of an acute stress would be an auto accident. You got in an accident, you're immediately injured. A chronic stressor might be smoking, where you smoke for 30, 40, 50 years before it dramatically impacts your health. That's something that happens over a very long period of time. In the case of a tree, you saw those trees that canopies had already died back. So frost or freeze damage is acute. It happens relatively quickly. Herbicide damage usually shows up in a matter of days or weeks. Those are acute stressors. Things that are chronic stressors. If you have, say, a pin oak planted in a marginal soil pH where a lot of the iron is bound up, that pin oak might always look a little chlorotic, and that's because it's just the soil. So yeah, there's enough where it can make photosynthate. Keep in mind, trees manufacture about 66% more than they consume, so it packs a lot away. So you can have a lot of variability in nutrient availability, and the trees still produce photosynthate. Is it producing 66% extra or 2% extra? Or is it even? Or are you in a deficit? When you get into that deficit, that's when you start to see a problem. So unfortunately, we're called out when people see problems. And by that time, it's almost too late unless they've just seen the problem. But we have to do something to turn that tree around to get it producing excess photosynthetes again. Let's just keep that in mind. So again, that would be a chronic stressor over a long period of time. Incorrect light. This happens a lot in our cityscapes where we have very tall buildings, trees that are planted in sidewalk cutouts. And you might not, these buildings are so tall that you might only have sunlight for 4 hours a day when the sun's directly overhead, or sometimes even less than 4 hours a day. So that could be a stressor. Long-term weather patterns. This is a big deal for post oaks. Post oaks are somewhat drought tolerant, but once the drought has lasted long enough, well, there's pretty much nothing you can do about it, and your post oaks start dying off right away. Improper soil pH, again, you're binding up those available minerals and nutrients. And site selection and adaptability. We all have some ability to adapt to our natural environment. But if we get outside of that, it just exceeds our genetic ability to tolerate it. So it becomes this long-term stressor. Some examples of abiotic disorders, soil and site problems, issues with the root flares, physical or mechanical injuries, physiological disorders develop over a long period of time. Temperature extremes, you can have these frost cracks or a sun scald or total vascular degradation, as we saw an example of the big freeze. Defoliation can be due to hail. You can have competition. Rarely do you see grass, heavy, dense grass growing underneath the trees in a forest. And out on the prairie, rarely do you see forests or trees occurring on the prairie naturally. Trees and roots can produce, or trees and grass roots can produce chemicals that retard the development of each other. Another example of allelopathy is walnut trees. They produce a chemical called juglans, and that's the typical test question about allelopathy, is that the walnut produces this chemical compound that inhibits the growth and development of just about every other plant on the planet. When I was a kid, you'd go out in the forest and you would run into a black walnut and there would be nothing growing under it other than some moss or lichen or things like that, but there wouldn't be trees growing up under it. However, today, if you went out in the southeastern forests and looked, you would find privet growing everywhere, Chinese invasive privet, which seems to be immune to the juglans that the tree produces. You can also have pollution damage. There in Metro Atlanta, the ozone layer or the ozone levels have been increasing year over year. I'm sure something similar happens out in all of our major cities. But we had the white pines in the city of Atlanta for years and years that grew to be, 30, 37, 38 inches in diameter, huge trees. And then all of a sudden they started dying. And we realized that it was ozone pollution that was creating it. And so to this day, there's not very many white pines left in the city of Atlanta as a result. We can also have chemical injuries, systemic herbicides, or chemicals with phytotoxicity. I've worked on the Imprelis project for about 5 years. This company produced this product called Imprelis. It was a post-emergent herbicide that it was going to become the best thing ever made, especially for golf courses. It was an excellent herbicide, post-emergent herbicide. They could put it over their grasses and it didn't impact their grasses at all, but killed all the weeds. And it worked in really, really small amounts, like less than an ounce per acre, which is much less than an ounce per acre was the application rate. And so they were like, wow, we can get this stuff down. It doesn't take very much of it. It kills all the weeds. But they didn't study it long enough because a few weeks after the very first application, it started killing all their trees. So all of the white pines around the golf courses started dying, followed by all the Norway spruce trees that died. So all over our northern and midwestern areas of the country, golf courses where they used it, this product lost tens of thousands of trees as a result. So that's a systemic herbicide problem. Water availability. This is a big deal now is going to drought conditions. We have a lot of lakes that are going down, a lot of the soil moisture is decreasing. So the plants that can survive there are going to change. They're going to have problems. Another abiotic disorder is called a girdling. A lot of the trees that are developed in pots, these roots begin to circle inside of the pot. Once the circling begins, it really never stops. And so as the trunk grows and the secondary development of the xylem tissue year after year, it gets bigger and bigger. So do the roots, they get bigger and bigger. And so eventually the trunk runs into this girdle, this circling root, which is also growing in diameter, and one begins to choke the other. So you have a girdling root and the top dies. Another common example of this is just girdling, period, where they plant, the landscapers might plant trees and never come back and take off the stake, the guiding and the staking that they use to hold the tree up for the first 6 months to a year after planting. So as the tree grows in diameter, it incorporates the strapping and eventually chokes itself. So it was pretty common to walk into a backyard that had a bunch of Leland cypress, and the Leland cypress is nice and green until it gets up to about where I can reach, and then from that point up, it's dead. And when I get inside and look, I see where the guy line was never taken off, so the tree died from that point up just because it couldn't move enough nutrients or water to the top of the tree. We have some insects can create all kinds of damage. They can feed on the leaves. They can actually chew on the leaves. They can feed on the vascular tissue in the tree. Their egg-laying activities can also do a lot of damage. The cicadas that we've had the past year or so have this ovipositor that has almost like a saw blade on the end of it. It can slice the bark open and deposit eggs under the bark, but obviously anytime you're cutting into the bark, you're going to create some sort of wound that will lead to decay. So insects can be chewing, boring, or piercing and sucking. So it's you wouldn't really have one that bores into the tree and then sucks on stuff. He's just going to bore into the tree and eat the stored starches. You can have leaf chewers that just chew around like caterpillars that chew, and then aphids have a little stylet that comes out, can sink into the leaf tissue and go right into chloroplast and just start sucking photosynthate directly or starches directly out from the leaf. You can also have some that can skeletonize the leaf. This is where all the vascular, remember we talked about the vascular bundles inside of the leaf, the little veins that run through the leaf, and then in between the veins we have leaf tissue. So skeletonizers eat all the leaf tissue but don't eat the veins. And so you're left with what looks like a scaffold or a skeleton. A lot of these sucking and piercing ones produce a substance called honeydew. Remember that photosynthate is mostly a sugar. And an aphid just feeds and feeds and feeds and feeds. And because it's constantly feeding on a liquid, think about somebody out drinking beer all day, but by the end of the day, they're going to be peeing all day, right? So same sort of deal with this aphid. It's going to just constantly be drinking the sap. But in this case, the exuate, the emission from the aphid still has a ton of sugar in it because it couldn't process all that sugar. So it's just basically sugar. And that sugar is going to fall on whatever's underneath that liquid honey is going to fall on whatever's underneath where they're feeding. And because it's high in carbohydrates, everything in the world loves it. But one of the things that loves it is sooty mold, which is going to grow on the honeydew. A lot of people say, well, my tree has sooty mold. And I'm like, well, the tree probably has aphids or it has scale or something like that. So, remember that these things, the signs and symptoms can be different. Insects can also act as a vector. I talked about the Nematodes beetle being our insect vector for oak wilt. So this particular beetle is a sap licking beetle. So just sort of, you have a pruning wound or you have a lightning strike that exposes the vascular tissue and the tree begins to weep, this beetle is going to go and lick it all up. So here we have to paint our pruning wounds during most of the year so that the Nematodes beetle can't lick the sap after the tree's been pruned, because if they do, the disorder is on the tongue, and when it licks, it transfers oak wilt from tree to tree. There are also nematodes out there. These are microscopic worm-like critters, worms. It's a segmented worm. So these nematodes can get in, they're really, really small, so they can get in and actually inhabit some of the small root tissue, which can kill it. They can feed on root tissue, which can kill the plant. We also have mites. Mites are in the arachnid family. They're kind of interesting little critters. Most mites are beneficial, but some of them are not so beneficial. Some of these mites, some of the non-beneficial mites, they just suck with their piercing mouth parts and drain all the photosynthetic chlorophyll out of the leaf until the leaf looks bleached. There are other animals that feed on the bark. They feed on bark. They feed on internal tissue like xylem tissue. Some of them feed on phloem tissue. Think about woodpeckers, deer, and rabbits. Sapsucker is a type of woodpecker, so they'll go up and they'll hammer a little hole on the trunk, just deep enough to where it begins to weep, and then they come back and they lap it up, and they might make another hole right next to it. So if you ever see a line of holes in a tree, it's not a borer, it would be a sapsucker. And these are federally protected migratory birds, so there's really nothing you can do about them other than try to dissuade them from the tree by using something flashy aluminum in there, or wrapping their area with burlap, things like that. Deer can do a multitude of damage. They can rub the felt off their antlers, which tears up the trees. They can even just eat the bark if they become hungry enough. They can eat the tips off of the new growth off of the tree. Rabbits can do damage down at the base of the tree. They can take the bark off and get moisture out of the trees. Lots of things can damage them. We talk about disease and the plant disease triangle. So trees must be susceptible to the pathogens. Let's just take oak wilt as an example, because it's prevalent here in California and other places. So we have this pathogen that's out there. Do we have an oak tree? Yes. Okay, so now we have the pathogen, oak wilt. We have the tree that it can inhabit. Now we need the environmental conditions to be suitable for the development. So the nedulid beetle that transfers, we don't think about the root system, we just think about the beetle vector for oak wilt. It doesn't like warm temperatures, so right now, or this for the past 60, 70 days, it's been in the hundreds here in central Texas. And so the nedulid beetle is like, not me. So it's not really doing any transfer of oak wilt during these temperatures. So that's just an example of where it didn't quite click. But if it was in the 80s, well, then everything's clicking. The pathogen's there, the plant's there, the opportunity was there. Most pathogens are host specific, such as Dutch elm disease gets in elm trees. It's worse in American elms than Chinese elms, but it can get in each of them. Oak wilt can get into any oak tree, but it destroys a red oak in less than a year. It can kill a live oak in 4 or 5 years, and in the white oak family, it might just do 20% canopy damage, and then the tree isolates it and it doesn't get any worse. So it is, but it can get in the tree, but it can vary even within the species. The part of the tree that's affected is an indication of the severity of the disease. So this is sort of a generic way. If it's concentrated to the foliage only, then it's not going to be, we would say it's cosmetic. If it's not getting into the vascular tissue. But even foliar diseases can become a problem. So think about Photinia blight. It's just in the leaves, but these spores get into the soil and then are constantly around this plant. So every time the red tip puts on new growth, the new growth's immediately reinfected. So just because it's foliar doesn't necessarily mean it's not going to kill the tree over time. It's more of a chronic stressor than an acute stressor. Shoot and twig blight. We see in the Southeast and Georgia and the Carolina region, there has been an influx of this black twig borer. It's sort of migrated its way up from southern Florida, obviously further north. And it's a type of ambrosia beetle, but it likes wood that's about as big around as a pencil. So you'll see a tiny little pinhole on the bottom side of the twig. And from that little pinhole outward, the leaves die. And they like our southern magnolias as well as a few other things. So if you're driving around and you see some magnolias that have a bunch of tip decline, well, you might want to go in and examine for. We also have vascular wilt diseases, obviously. You can have root diseases, things that phytophthora and things that can just destroy the root system. Some diseases even require alternating hosts. So you might have, the common example is apple cedar rust or cedar apple rust. It spends 1 year in the cedar tree, and then the next year in the apple tree, and then back to the cedar tree. And it can look really cool. I think it's a really cool looking pathogen. In the cedar, it kind of makes this glob of stuff that looks like some sort of orange cancer that grows on the cedar tree. And in the apple tree, it makes the leaves look like a calico cat. And so from a distance, the apple tree can look pretty cool, but it won't produce much photosynthate. Eventually, it could impact your apple crops. Keep in mind that fungi are responsible for the majority of plant diseases out there. Know if something is a bacteria versus a virus. So viruses, there really are no cures for viruses, as we should all know by now after several years of COVID. Then we have bacteria out there, and bacteria respond to antibiotics. Viruses do not respond to antibiotics. Management of plant disease is an exercise in prevention. Most bacterial, viral, and fungal problems, once the tree has them, it's very, very difficult to eradicate from the tree. So then it becomes a management issue, something you're going to have to manage for the rest of that tree's life. There are some things that you can prune out. So if you can effectively prune it out using sterile techniques, well, then you go back to 0, 0, 0, and then it becomes a matter of prevention. But most of these things are very difficult to get out of the tree. And so preventing it from ever getting in is much easier than trying. You'll never cure it. Global commerce and travel have increased the importation of non-native species of insects, diseases, and invasive plants, such as our lantern flies, our Asian longhorn beetle, the emerald ash borer. There's just a host of these things that have been brought in. They have no natural predators, and so they just explode in the right environment, destroy a bunch of our trees. Look for laboratory assistance. A lot of these things, the bacteria versus the viral problems versus, say, things that can give you the same appearance, you'll want to test them. And most of the universities have run these extensions. The local, your local extension office can tell you where to go. This course is obviously developed in Georgia, so we've got our University of Georgia, but every state has this access. There's also the United States Department of Agriculture has laboratories as well. And there are also private laboratories available, but they're just much more expensive. So we want to talk about what you send them. A sample should be taken from a representative portion of the plant. And by representative, this is usually what we want is a transition area. Like a good example of a transition area would be where I talked about the black tip borer on the magnolia, and I picked it up, I looked on the bottom, and I saw that little spot on the bottom, that little hole in the bottom. It's dead on one side, green on the other side of the hole. So my representative area would be a section of the green and a section of the dead, and I would send that in for diagnostics. And they would get it, and they would look at it, and they would say, looks like a black tip borer, and they might slice it open, look on the inside, and find it. So that's something I could have done myself. However, I might not be able to tell the difference in other pathogens in the tree. So like oak wilt, is it oak wilt or is it a drought problem? Is it oak wilt or is it freeze damage? There's a number of things that it could be. Is it fire blight or is it bacterial leaf scorch? That's an excellent example. It's something that can look kind of similar. So take a section that's alive, take a section that's dead, take some of the dead tissue. If you see something that's oozing, it's wet looking, it's sunken, it might look like a canker. You might see something growing on the edges of the bark around the dead area. Send all that stuff in. That's a representative portion. And then if you think, like here, we think it might be oak wilt. So when we package up oak wilt, we have to put it inside of a cooler with some ice or dry ice or something that's going to keep that sample cold so that it lives. Because you remember I said that not only does the Nedula beetle not like high temperatures, but oak wilt doesn't like high temperatures. And so the pathogen might die. And when it dies, their test that they perform to look for it might not work. So make sure and get a fresh representative sample. Ship it very early in the week. Ship it on a Monday so that it gets there in a few days, and they'll open it up and they'll begin processing it. If you send it like on Thursday, it might not show up until Friday afternoon, and then it'll sit there. It might even sit outside of the door of the lab until the lab opens up again on Monday morning. So you can have all kinds of environmental problems that happen during those time periods. So send it in early. And one of the most important things is give a very detailed description. I worked in the pathology lab in Colorado for a few years, and I'd get these samples in and it would just be a stick. There was nothing else in the package. It didn't say what species it was, where it came from. It didn't say what they were looking for, none of that. So it's like, well, what the heck do I do with this? And so I'd either have to just throw it away and never do it, or I would have to track them down by phone and get all the information from them. So give as much detailed information as you can. Most of the extension services have a form. You can go to their internet site. It'll have a form for you to fill out and send the mail in with the sample. It'll ask you things like, when did you collect it? Where is it collected from on the tree? What species of tree is it? What are the environmental conditions like? Has the tree been irrigated or fertilized? Things like that. Then it'll have a section, what do you think it is? So I would say, well, I think it's oak wilt, but I'm not sure. So each one of these tests that they run is a very specific test for a specific pathogen. So if you just send them a sample and don't give them any clues, they might have to run 6 or 7 different tests to identify your pathogen. Like I'll send it in and I'll say that it's oak wilt. They test it. It's like, sure enough, it's oak wilt. So they confirmed my diagnosis. However, they might run an oak wilt test and come up with nothing. And so then they might come up with something else. Well, maybe it's verticillium wilt. So then they would run a verticillium test and say, oh, look, it's positive for verticillium. So then they would send information on verticillium infections, which were treated differently than oak wilt infections. So be absolutely as detailed as you can make it. And like I alluded to earlier, rarely is the real problem a simple matter of isolating a fungus or identifying a pest. Oak wilt just happens to be one of those things that, okay, I see it, I can treat it, and I can prevent it, but I cannot cure it. So it's an invasive thing. It's just new here, so that is the real problem. However, most problems come about because the tree is under some type of chronic stressor. It's having to spend a lot of energy to overcome chronic stress. And it might have been doing it for so long that it has no stored starch reserves anymore, and it can't spend chemicals for defense. And so then you get all these secondary issues that come about. So that again brings us towards the end.